my pleasure to announce our speaker for the MIT EI seminar series. And that speaker is Marija Ilic. She received her Doctor of Science degree in Systems Science at Washington University in St. Louis in 1980. She's currently a professor at Carnegie-Mellon University with a joint appointment in the Electrical and Computer Engineering and Engineering and Public Policy departments. She is the director of the Electric Energy Systems Group. She is also the honorary chair professor for Control of Future Electricity Network Operations at Delft University of Technology in the Netherlands. She was an assistant professor at Cornell University and tenured associate professor at the University of Illinois at Urbana-Champaign. She was then a senior research scientist in the Department of Electrical Engineering and Computer Science at MIT from 1987 to 2002. She has 30 years' experience in teaching and research in the area of electrical power system modeling and control. Her main interest is in the systems aspect of operations, planning, and economics of the electrical power industry. She has co-authored several books in her field of interest, and she is an IEEE fellow. So please give us a round of applause for Marija.
Thank you. Thank you very much for coming. I really don't know the background of people, so I'm going to try to make this as not too technical. But if there are questions, clarification questions, or any comments, please feel free to. We'll make it as interactive as you wish. I don't know who is why in this room, but a lot has changed in this field. So it used to be that we did things one way or the other in electric power grids, and then a lot changed, and there is a lot of research money, from the current stimulus money, etc. And then it's no longer clear what are the things that really matter, things that don't matter, and so I have actually organized my talk around that question. If we just remote ourselves and rethink the operations and planning of today's power systems, why do we even need all this high tech, that needs to be embedded? What difference it would make, and how would we do it? So it is with that in mind that I have organized my talk. So based on the title, you see that I want to talk about how do you enable physical electric power systems to operate better using information technology. And the first thing is that we will argue is that integration is important. And that would very quickly drive us into a particular way of doing things, pretty much the way we have done things, and then there is nothing new. We will argue in this talk that actually there are many, many different ways of integrating. And that's one thing that I want to emphasize and actually explain what are the implications of that integration approach on performance in different power systems architectures that are evolving. If we can just narrow the whole thing into one or two technical ideas, is the idea that I want to talk about is that this notion of interaction variables within a complex electric power grid is if we define these interaction variables the right way, we can actually begin to relate things that we have not related in the past, the engineering solutions to sustainability, for example. And I want to share with you some of the things that I have learned recently from the work by Elinor Ostrom. How many people know who she is? Two of my students. Elinor Ostrom was the first woman Nobel Prize winner in economics. And she actually sort of turned upside down a few years ago the basic principles in economics, arguing that you can manage tragedy of the commons in very different ways, in a sort of bottom-up way, rather than managing it as externality. And so she has begun to apply those notions of managing things and looking at the social ecological systems, water systems in particular, from that point of view. How much can you do in a different way than we've been doing in terms of preserving the systems and making them sustainable? And she talks about that and has a very active group in Indiana where she teaches on water systems. I have been doing work last 2 years on the energy system, sort of asking myself the question, what does that mean for energy systems? And I want to share this with you. It turns out, to me, I found it extremely interesting that the way she poses the problem of sustainable energy systems, sustainable socio-ecological systems, is that you can actually think of any system as having some core variables, having some second-order variables, and if you understand those characteristics of those variables in any ecological, socio-ecological system, you actually can predict how sustainable the system is. It turns out that that is not enough. You have to actually you have to capture these interaction variables between the core components in a socio-ecological system in order to actually make the most out of the system, which is initially maybe not sustainable, fully sustainable. And I found that to be extremely interesting because I think ultimate goal of improving electric power systems would be to put more intelligence to actually enable more sustainable energy utilization. But wouldn't it be nice to connect that notion of sustainability and how you define the sustainability of any social ecological system to things that we do in engineering, how we model our interaction variables between different components, and etc. So I think my talk is sort of going to draw this parallel between and the interplay between interaction variables for complex technical power systems and IT, how IT can shape interaction variables in a physical system, and what implication of controlling those variables would be on making the energy system sustainable. It is really a tough connection to make, but I will try to argue that. And then I will illustrate this sort of really abstract concept on several representative electric energy system architectures. And sooner or later it becomes clear that these interactions have between different portions of the complex system have different nature. They can be temporal, spatial, or contextual, and I will talk more about contextual. And one way to get into scalability problem, into role of IT, would be by understanding these interactions and the complexity that comes from temporal, spatial, and contextual interactions. Then, once we do that, I want to sort of take a step back and say, look, we've been doing this in traditional power systems for so long, and what does this actually mean for the way we've been operating the systems? Can we operate the systems better, today's systems, without adding new technology? Can IT fundamentally improve performance of today's architecture? And then say something about the evolving architectures. So I think this very likely is not news to anybody in the room, that there is pretty much a massive integration, massive effort at the US level and worldwide on integrating communication systems, control systems, rethinking economic and policy for the changing electric energy systems. And this really opens an opportunity for people who work in soft high-tech technologies. But what we see is that the hardware is already being deployed, but sort of rethinking the integrative software to enable those the hardware to better fit into the legacy system is sort of trailing behind. So I want to talk about that. Again, as I said earlier, this is again, a lot of this is work in progress, but I think it's very important, so I wanted to share with you. So when we talk about integration, you talk to the traditional power systems, and they understand exactly what integration means. It means top-down, I plan, I have full information, and I schedule things, or I'm fully in control of everything. If you talk to people who come from different disciplines, they're going to say, well, I can actually achieve integration many different ways by designing complete electric energy markets. We have not designed markets. We have done something. We really have not designed them for performance. There are a lot of people at National Institute of Standards, people working on interface standards and protocols to integrate. That's really not top-down. So there are very, very different ways of thinking about integrating future electric energy systems for some performance. And again, one of the questions that boils down how much coordination you need to do. If you think about the entire US interconnection energy system, how much is the responsibility of the federal level to coordinate, how much you can do distributed state. There are many examples of this, but the point being here that you can actually do coordination in very non-traditional ways than the ways we have grown to think about them in power systems, and that opens the door to many disciplines, to distributed control, to distributed communications, etc. And so everybody is talking about people who know those tools. They're saying, well, we can apply them. People who have good hardware, they're saying we can put good hardware on. But there is really no an overall school of thinking on how to do this. And the challenge is to capture all of these interdependencies. So one way to begin to think about this is, again, as I said earlier, the objective ultimately is to have intelligent physical electric grids enabled with IT to somehow enable more of sustainable, in this case, energy systems, social ecological energy systems. If you look into what we know, people who worry about climate change, they use some fragmented, fairly coarse models of these energy systems. You know, they have certain relationships at the very general level. Then you talk to power engineers, they're talking about fragmented models of detailed engineering grids, and they are interested in answering different questions. And in the middle of that, you don't have the models on either side that talk to each other, and then you need now need to design this IT for smart grid in order to enable, a sustainable energy system by doing a good, smart engineering design. So it's clear that we have to really worry about the possible modeling approach first. Okay, so this is our working definition of sustainability and how things have changed in the past. This is what the power grids have done. They schedule supply to meet given anticipated demand. You provide electricity at a predefined tariff. You produce energy subject to constraints. So everything used to be single optimization subject to a lot of constraints. And the consequences of these are many. Or everything that was constrained becomes an externality. You can't give incentives, etc. So the story is very long. I think that in order to have a sustainable energy system enabled by smart electric grid, you really have to begin to think about adaptive reconciling of trade-offs, and that effectively becomes a sustainable system, which accommodates a lot of choice, if you wish. So you don't schedule supply for predicted demand. You schedule supply to meet demand in which both supply and demand function are given. So there is a choice from the demand side. You provide electricity at quality of service determined by what customers want to pay, etc. So it has been a really qualitative change here, and you can go down here on many attributes now that become attributes, and you can have different trade-offs depending on what the users actually need, in contrast to being having single optimization. It minimizes total generation cost subject to everything else being constrained. So this is what we mean by sustainable. Okay. So why is this so hard? And I have to admit, after 30 years of being in this field, and I think I know power systems pretty well, it's actually hard to take the step back and identify what is the difficult question, and if we were to make some links there, maybe we can make some progress. This is what this talk is about. So I think in a nutshell, the most difficult question in designing IT for energy systems is how to establish sufficiently accurate but not too complex modeling framework which captures interdependencies between energy, social ecological systems, physical grid, its IT, and the governance system. We really have not done that. and there is no school of thinking. And so, again, as I said before, if you are doing climate change, you are doing very coarse models. If you are doing nitty-gritty frequency regulation using different models, how to put them all together. But the objective of all of these, and the objective of using IT, would be to match the attributes of energy socio-ecological system by designing around given energy system. So in other words, you have some, I'll explain in a minute, you have some energy resources, you have users with their needs, and now you want to somehow match them with the physical grid, and it's IT, and how to do that. And I will argue that one possible way to proceed by actually modeling what matters and not being too complex would be to think in terms of these interaction variables. And with different students at CMU have been working over for different time scales, but pretty much the same idea on how would you actually do sufficiently good model for whatever. How would you do a good model for power electronics control to stabilize, your kinetic energy in your generator? You can think about that problem on one time scale the same way as you think about scheduling at a different time scale if you think in terms of interaction variables. So it's potentially generalizable. And it's not all done, but I will share as much as I know. And then the whole problem then boils down to the question of, if I model my system in terms of interaction variables, then I design IT to support performance of the interactions between the system. And that goes across temporal, spatial, and contextual. OK, so what does this mean? It was heavy, and it's been heavy for me also, so I had to explain it. But if you think, this is actually not that new idea. If you talk to engineers, this is their one power grid, it's another power grid. These are the power plants and the loads interconnected. But this utility is actually electrically connected with the other utility, and they exchange power. There are no electronic valves here to actually directly control the flow unless you have DC lines or power electronically controlled flows. But in principle, if you have a disturbance here in this power area, in this utility, you're going to see it in the other area. That's the interaction between the two control areas. So we know how to do well that. I have spent a lot of time actually in formalizing these models for hierarchical control and the technical side. And this is what you're going to see it. You're going to see it at the time scale of seconds, for example. Now you go and say, so just sort of more formal definition, and I don't have time to spend on the mathematics of this, but I could give references to people if people are interested. Interaction variable associated between particular subsystem and the rest of the world is a very particular combination of internal variables, state variables, which doesn't change if you disconnect the subsystem from the rest of the world. So it has a very good technical definition. And so for people, for example, who do automatic generation control, that's your ACE, area control error. You control that the total imbalance between the subsystem and the rest of the system. And if you capture that, rather than each particular imbalance inside the area, you have a much less complex model. And now comes this socio-ecological system. I want to model my engineering system. I want to design the power grid and its intelligence so that I actually make the socio-ecological energy system sustainable. So this is directly from the work by Elinor Ostrom. If you think about it, it's a very similar thing. She says, I have resources in the system. I have some governors, users, there are interactions between them, but they are at a very, very different time scale and very different coarseness. And what I found fascinating, and I've been playing with this now for 2 years, so I think it's time to come out of the closet and talk about it. So this is your social ecological system. You have resource system, resource units. These are what she calls core variables in any social ecological system. There is particular governance system and users. And these core variables, there are only 4 of them. for any social ecological system, for water, for energy, whatever you choose, they have these second-order variables that characterize the nature of the resources according to size, productivity, predictability, or even mobility. Do I have electric vehicles, or I have, some stationary resources? Then you different socio-ecological systems differ depending on what are the governance systems you have. In particular, it's important you have collective choice rules. And the users, this is very new for energy systems, for power systems. What is the number? What is the leadership? What are the social norms, etc.? So now this is again from her work, but the key role of interaction variables in any social ecological system is now define the core subsystem variables, define second-order variables. In other words, what are the characteristics of these resources and users? And then use these second-order variables to determine how likely is the social ecological system to be sustainable. Well, when is the system going to be sustainable? When resources and users match, when they're aligned. Okay? So what happens is, if they are not aligned, is that these deeper level variables have to account for explicit interactions between the subsystems. In other words, if I have a nuclear plant which is base unit, then the users better shape their peaks so that they come together, that they balance and they match. And so actually the engineering interaction variables come very well together with the socio-ecological core and second order variables, but we have not thought about this way, and I think it could be very helpful. Takes one very long way to linking the objectives of designing the physical grid and its intelligence to the overall objectives of the sustainability, sustainable energy systems. Another thing that we forget, because we all like to do our modeling, we all like to do our designs, there is no single model for everything. There is no single control design for everything. So the choice of second and deeper level variables really depends on the questions of interest, over which time scale I am, what am I trying to do. And matching the attributes of second and deeper level variables is very important. What that means, if my resources are not mobile, I need that physical grid to bring it to the users. And so deeper or level variable is the interaction variable. Okay. So I drew these recently, it's proceedings of IEEE, now January 2011. So one way to put this all together is to say I have these energy social ecological systems which have the same type of core variables as any other SES. And then there is a man-made grid, which is the physical network connecting energy generation consumers, and it's needed to implement interactions between the resource among the core variables. And this grid is going to have its physical design, but it's going to be more or less smart depending on what I need to do with the core variables in my system. So our conjecture has been that design of the smart grid, not any grid, but the smart one, is the man-made power grid. It's IT and governance system, which really requires the introduction of these deeper level variables for more effective differentiation among the resources and the relationship between the resources and the users. And what also we have to recognize right in start is that different energy system architectures that I'll show you have very different relevant technical interaction variables. So in order to design IT, we really have to come up with a model that matters. And you have different model that matters in one architecture than the other. So this is how it all comes together. Let me show you the examples, more specific examples. So if you think about what has happened in the power systems, historically, we've had bulk electric energy systems fully regulated, bulk electric energy systems restructured, hybrid electric energy systems in which you have large and small resources, and then fully distributed energy systems for developed countries and for developing countries. All these architectures are very, very different. And I don't know how far or how fast I'll go through my talk, but at least I want to make sure that I illustrate the main messages. So in a fully regulated bulk electric energy system, you have these very large, not mobile resources, generators far away from the loads. And there are objectives of individual utilities, and they can maybe exchange power or not, depending on, there are no electronic switches unless you have DC lines. And more we are having these distributed resources which are coming closer to the end users. So in the unbundled regulated utility, you have power suppliers for themselves. That's interaction between power suppliers, sellers, very different interactions. Here, utility is in charge of all of them. In the restructured one, power suppliers are sort of nested inside utility, and they can be decision makers from themselves. And so you really don't have one-to-one mapping between the markets and the physical system anymore. This is the future network. You've seen a lot of pictures of this. Now you have very, very different distributed technologies, and they're much closer to the end users. And so this is a very different architecture than the one with very few, very large generators. And so I can redraw these new architectures basically as either being hybrid electric energy systems in which I have portfolio of generators and users with their own objectives, but they are not necessarily utilities, and they are interacting weakly. And so the whole point of this exercise is to say that interaction variables between different portfolio will be different than interaction variables between the players inside the utility. And then for some people are saying I'm going to have everything, fully distributed control everywhere, the household level, etc. So clearly, even if you don't do the math on the interaction variables, it's clear that this guy is really in the noise relative to the rest of the system. So he doesn't have to talk much, or he's not interacting that much with the rest of the system. So what we need to monitor and control is going to be very different than what you need to control in the large systems in which power has to come from far away. Okay, so let me try to cover at least the case of the traditional power systems. So again, this is really a hindsight view. I didn't think about this, as we were doing it. Actually, the spatial, temporal, and contextual interactions are very significant because you really have these large resources. Users are not doing much in the regulated industry, so you have to have significant interactions and power transfer and intelligence between resources and users in the traditional regulated industry with large resources. These interactions are even stronger when you have economic transfers between utilities, etc. However, if you look at the literature, and this is a story in its own right, is the entire book, assumptions are made for simplifications. So we operate. This is the only way that the complexity of the interconnected system, bulk power systems, has been managed with relatively little IT. Has been because we assume that these interactions are weak across time and space and context. And so as a consequence, and I'll give you just a few examples, but as a consequence, it's very hard in today's industry to be at the same time reliable and efficient, because you actually squeeze out efficiency through interactions, and that's where IT helps. But if you assume there is no interaction, there is no efficiency. Okay, so it's very temporally complex. It's spatially and contextually concept. This is your picture of the network representing New York. This is New York, Ontario, New England, equivalent system, Pennsylvania. And you see these different colors. These are different transmission owners. And they all coexist within one interconnected system. So there must be some interactions, and we used to spend a lot of time modeling these things and running the analysis to see if the whole system can exist and what are the voltages, are they acceptable, is the system stable. This is a huge monster simulation. This is what most of the software IT in today's electric power industry does. However, software is complicated, but at the same time relatively simple, because it really draws on these very strong assumptions that each control area schedules its own resources. There exists the solution exists to the interconnected system. While I'm doing my own, there is sufficient voltage support that the slow deviations can be regulated, frequency can be regulated control area by control area, etc. And also the primary controllers, which only exist at generation, there is no control anywhere else, they stabilize dynamics very fast. So you have this fast stabilization, which is local. You have regulation of frequency utility by utility, and then scheduling control area by control area. So the time scales are very separate, not correlated, and also spatial separation is in place. And so basically we simplify by ignoring the interactions. And what happens during the blackouts is that a lot of these assumptions get violated. And there is a lot of literature that documents that. I don't have time to go through details, but basically the translation of this is that there are large spatial and temporal interactions which are neither monitored nor managed at the interaction level when you have large changes in the system. And because of that, there is no, you have very, very hard to anticipate outcomes at the interconnection level. So this is what happens. You assume that this is disconnected from this, but during the blackout, you had really huge circulation of power. These are your interaction variables at the very large coarse level in the Northeast. And this is where IT comes in. Because of lack of ability to manage interactions between generation T&D resources, we actually have had this blackout, and it's documented quite well. Again, don't have time to go into details, but there are some really interesting numbers that people have come up with. So the part of the problem occurs because there was shortage of power here, excess power here, and then the power was trying to go from Pennsylvania to New York, and actually the power transfer could only manage so much. And so the Pennsylvania was not coordinating with New York, etc. And so basically, the minute you cannot transfer power that's being produced here and loads are not reacting, you have excess power and frequency starts collapsing after protection disconnects other devices. And that takes time, like several hours, but that's what happened. So clearly, you have a case here of very strong spatial and temporal interactions, which today's software can't manage. If you were to do some very simple things, if you were to coordinate real power generation in the neighboring areas, you can increase, I believe these are just numbers I'll go very quickly over. The interface, if nobody does anything, so there is an outage, let's say in Pennsylvania, New York doesn't know about this, the interface limit between New York and PJM is 100 megawatts. If the other areas knew and they rescheduled their own generation to support that outage, the interface limit would be 1,200 megawatts without building any lines. That means there is a very, very significant throughput that you can manage if you knew what's happening on the system and reschedule something in a more coordinated way. Voltage scheduling is very significant. This is for people who are into voltage. You can actually increase that interface another 1,000 megawatts. And phase angle regulators, power electronics control is just magic. It actually changes the electrical distance exactly where it should change, and the throughput goes to 8,000 megawatts. That means, so when we talk about building new transmission to deliver power, wind power from Dakotas to Atlantic states, we better think about this, because you can either build, I think they're talking about 200 billion watt wires, or you should think about how to use these wires that you have. So that all sort of points out to the direction that now becomes a general theme, even as for the changing architectures. And the theme is that you have to, because of complexity, you have to begin to have multi-layer, multi-directional coordination within the interconnection. And this in terms of interaction variables, and you model them that way. In other words, you don't have to exchange the full information between every single detail, but basically you exchange only the minimum if you model your system in terms of interaction variables. So just some examples again of depending on, in different scenarios, depending if you support the voltage or you don't support the voltage, if you have scheduling by neighboring areas, these tie line flow limits between New York and PJM, et cetera, they can change so significantly. That's unbelievable. And that's what IT is doing. Okay, and also if you think about the typical, typical temporal change, the real power tie line flow exchange between New York and Ontario, for example, as a function of controlling different gadgets like settings on low tap changing transformers or capacitor banks or settings on generators, you're going to get very, very different tie line flow exchanges given the same wires. Okay, so this is sort of the way it's been, and the point being that even in today's industry, I think we can do much better if we actually tighten up our modeling and do very little coordination, but not too much in terms of understanding really what the interactions that one needs to monitor and control as conditions change. This is very new, and I know there are some people here who are working on that, so I just wanted to mention. Now there are these Phasor measurement units, which are effectively very accurate and fast measurements that you can put on the system. And the question is, even on this simple system, here is the disturbance that you want to manage. Where to put the measurement? Or this load, once the measurement is done, should it talk to this control on the generator or the other? These are all very clear, control questions and IT questions. And so the point being here very quickly that what we have done in the past in today's industry is for schedule. For anticipated demand, you schedule generation. And now with these fast measurement units, you can actually manage the unanticipated fluctuations around the schedules, very fast ones, and still maintain state variables within the acceptable limits. Let's say this is voltage, 5% deviation during the outage. If you have particle control and you have particle sensors, if you just have one sensor, this is what's saying for this simple example, you are still going to have violations of your acceptable voltage. If you put two measurements and design your control right, you're going to stay within the acceptable limit. It's unbelievable how much the control can buy you, but actually this example is the first one of its kind on closing the loop with PMUs for control. We are just doing pretty much PMUs for situational awareness to know what's happening on the system, but not for closing the loop. I'm arguing that you really have to close the loop in order to take advantage of what can be done. Okay, so there is a lot of hidden value of smart IT-enabled transmission system management, even in today's industry, in regulated industry. And some estimated benefits are 3% loss reduction, 3 to 5% increased efficiency, and this one is huge. 10 to 20% decrease in reserves that you don't have to have because you would basically react just in time and just in place. In other words, you would be moving from what is known now as preventive worst-case design to you have standby reserve just in case something happens, or you adjust other resources when the contingency happens and you don't have to have that reserve. 10 to 20%, FERC has estimated these numbers. This is huge. So one has to begin to play that game when you have a lot of uncertainties on the system, either outages or intermittent resources now with new systems. And there is a potential to squeeze much more out. So this is all even before we started talking about the new architecture that is evolving because of distributed generation. it looks like, you know, it would be nice to do, and there are potential benefits, but there is a lot of work to do on design of IT. As I said, that the whole thing evolves around capturing the right spatial and temporal interactions to have this right trade-off between reliability and efficiency. That requires careful modeling of interaction variables. New platforms for converting data into information is huge. You know, National Science Foundation has a program now that's starting on sustainability just on this thing. How we have so many measurements. What are you going to do with the measurements and convert them into what information? I'm arguing that for purposes of inducing sustainability through the smart grid, you have to actually somehow convert whatever you are measuring into reliable information about interactions, temporal and spatial, but very likely there is much more there. And this thing is also huge. You know, if you want to push the system closer to the limits to do what I'm suggesting, you better have to develop good verification models, verification of models that are used. These techniques have to be used as the system status changes. If you know something, if you have large outage, your model looks different. How do you update that based on the data online measurement? It's huge, and we don't do that very well. And again, there is not much of user-friendly software. So this is in the nutshell. This is really the status in the regulated industry. There's a huge potential for IT, but actually, you know, one has to walk very, very carefully through what matters and what doesn't matter. Now, just a little bit about the new architectures. So I think everybody is talking about it, sort of understood. But again, I want to tackle it from the same angle that now we are having much more of actions at the customer automation side. We have potential for much more communications. We can have direct light flow control devices, DC lines, etc. So these are the technological advances, microprocessors. Everything has come down. Sensors has come down to cost-effective, you know, reliable technology. So what to do with it? And at the same time, some parts of the country have gone through organizational changes. So depending on what we are doing, again, the architecture is different. In the restructured industry, before we put new devices, we already are in the domain of decentralized decision-making under uncertainties, right? Because if you, here you have transmission owners, you have generators, loads, they're all deciding for themselves and somehow interacting. So there is additional source of complexity. There is interaction, heterogeneous interaction between the physical system and the economic signals. And again, you can generalize it because there is nothing that says that interaction variable has to be just a physical variable. Timelines are, again, now even more complicated than in the past because we have the interplay between technical decision-making and the market decision-making. And one big thing that I'm sort of stuck on is that what we have done so far in the US is we have these spot markets, which are day ahead. So there's very little transparent information about long-term in the future. And I want to argue that this is one thing that we must capture if we are going to have efficient markets for the design. But before I go there, I want to point out that you remember how I was talking about different technical outcomes if you have this type of control on the system or not? Well, the prices and the generation costs and everything is very different because we have locational prices. They're going to depend very, very much on how I control the system. And so there are some scenarios here. Scenario A means utility just does it itself. It doesn't coordinate with anybody. This is the ideal case. If I were to optimize to have one electricity market for the entire Northeast, well, if you have a very clever coordination of control areas with very little minimal coordination, you actually can come close without having to actually manage everything in a single market and so forth. And actually, when you do that and support voltage, you even improve cost even further. And similarly, it has implications. How you control the system has implications, generation revenue, load cost, etc. So the role of the transmission grid is really changing now. The transmission grid becomes an enabler of these objectives that we have talked about before. And only one thing that I would like to point out about markets, and this is this problem about managing uncertainty. So we are not that much now on interspatial interactions. We are more on intertemporal interactions and uncertainties, which come with markets. And there, I just want to give you the case that for me was a striking case. In the North Pole, people have both spot markets, which is day ahead, and financial markets with 3 years in the future. And this is how the market clears over different time horizons. It's transparent. So you can look at the historical spot prices in North Pole. You look at the historical future price. These are anticipated prices due to the long-term forward markets. And you look at their difference. And this is what happens. This is all the arbitrage, the uncertainties that you see. You cannot invest well because you don't know what's going to happen in the future. And one way to capture that, this is work with Odon Oberud, Botterud. These are real data, the only real data that I know of. Depending if you have forward market 1 week in the future that clears 1 week, 4 weeks, etc., you're going to have different standard deviations, which are larger and larger as it's expected. But all what it's telling us is that there is a major need for longer-term forward markets in the US. You can't get away and be efficient with investments unless you have just spot. And people just choose to ignore it. And again, it has to do with these temporal interdependencies and the efficiency that comes from temporal correlations, which if you don't know, you're going to overbuild without taking into consideration what's going to happen in real time. Okay, so this is on markets. I did the regulated one. I want to just say maybe 5 minutes something about the same thing happening when people talk about truly smart grids, when you have wind power and adaptive load demand, etc. We have to begin to think again here. It really comes down to the problem of modules of one sort or the other sort interacting and capturing either physical or financial interactions and through the information. And depending on what is captured, how these modules talk to each other, you are going to have better or worse performance even in the distributed system. One thing is for sure that if you have a truly distributed system, these interactions are relatively weak. So it doesn't buy you much to coordinate. And this is why people think that you just self-manage yourself and you're done as an agent. Well, if this is a portfolio of a few things, then that interaction between the cluster of small resources and some other cluster may still be significant. And the question is how to model that and when is the threshold that, okay. So this is again interesting from the point of view of, what IT you need to embed into which level in this distributed changing industry. So basically you have smart components and smart control at all levels, supplier, user, transmission. And one thing that we have to understand that this is really not equilibrium condition anymore. You are not doing static optimization. That it's potentially optimal long term under uncertainties, but it is a result of multi-stage distributed decision making by different users. And IT tools will play critical role to facilitate that interplay between different entities. So we can go one by one, but just as an example here. Smart power producer, he has his own goals, profit maximization and risk management. He is going to embed IT, which is decentralized stochastic optimization, some agent type technology. But his different technology that he has locally, storage or combined cycle power plant or whatever, is going to depend on the industry structure in which it coexists. It depends on how much he connects and how much he interacts with the others for efficiency. So that goes across the users and smart networks. And I think in a nutshell, this is what very likely happens. We are going towards flexible open access integration, which is really a change of paradigm compared to the hierarchical control that I was talking about. So you have models and intelligence at the distributed decision-making level. And then one employs just communication to provide the relevant information online. System users observe the status of the system and internalize into their distributed objectives, and this is how coordination happens. And IT just makes it happen. It's a sort of make auctions work. I want to end up by just a few pictures. So if you adapt this interactive distributed paradigm that you can embed a lot of intelligence, we call them diamonds, dynamic monitoring decision systems. You can put them into households, groups of households, into different technologies. So you need model, you need your own model and your own decision variables. If you decision tools for the anticipated or exchange information with the rest of the world, then you do your decision making, then you tell the higher level entities, maybe control center here, you say how much you want to consume and what price, for example. But after you've taken into consideration the startup cost, rate of response, etc., you've internalized that. So the information that you give back to the system operator is so simple that he can actually use the existing tools for clearing those bids and still clear the market. So the system can evolve. This is not really radical. And so the basic idea that we are pushing at CMU is distributed management of temporal interactions under uncertainties, and then adding those and interacting with the existing tools that you have on the system, at the system level. So let me show very quickly what this means in words. So power system with the conventional generation, you want to put wind. This is Lucy. He just finished his PhD thesis on what intelligence you have to embed into wind power plants to operate the system better. So this is what happens. If you have predictive control at the wind, you have model predictive control, you control the wind blades, or you schedule over a unit commitment in a distributed way, you are actually going to find some really fascinating things. That this would be the wind that you would just send to the grid if there were no, if you didn't have additional decision making. However, you adjust and you don't send all the wind because you don't get paid for that. And at the same time, you can store that wind locally. The consequence of that is that you don't have to run your fast gas power plant nor build it. You just have very little use of gas power plant. This is unbelievable saving just by internalizing the temporal constraints at the distributed level. And it has consequences of how you schedule your conventional power plants, because if you look ahead at the distributed level for anticipated conditions, you can begin to ramp up even if you are a slow power plant, and so it goes. So you can actually better utilize even the conventional slow assets when wind blows. And then you actually gain big way if you combine wind with responsive demand. And so JY is doing her PhD thesis on that. We are very fond of it because basically what happens is, again, if this is your anticipated demand, system demand, when wind doesn't blow, if you have price responsive demand, demand just dips in when the wind doesn't blow, and you don't have to build anything else. So they come together through the right interactions. Consequence, again, that you don't have to schedule gas plant to be very picky. And the estimates here on how much you save on investments and and expensive fuel are really unbelievable. I think we need to get, this is an IEEE example, but we have to go to the real systems to see what that means. Nick did this for electric vehicles. Electric vehicles are, for all practical purposes, just adaptive demand, and this figure has been shown many times. But if you have electric vehicles which just do fast charging, the electric load that utilities see may be such that they have to build new power plants. If you do just a little smart, you don't have to build new power plants. And so just, again, some hypothetical simulations, depending on what penetration of electric vehicles you have, you get very, very different outputs, but you squeeze sort of just in time and just in place the resources through the right interactions. And I think that this is where I should stop. It's just about time. But I guess I would like to just close by saying that we are very likely moving into an environment in which there's going to be a need for a lot of smart aggregation and then interaction within. Here, you cannot separate the effects. It really pays off to build portfolio and to interact, to work closely in a cooperative way. And then there are weak interactions, or you can still gain something from the weaker interactions. But this architecture for IT is very different than the organizational one or the one that we have right now. So I stop here. Thank you. Any questions? Yeah, please.
I was just wondering if you could tell us how some of the simulations were done.
How?
How some of the simulations were done, showing the chart.
Okay, so for the regulated industry, there are really large-scale optimization, nonlinear optimization tools, in which if you want to show the effects of voltage optimization, you really have to run nonlinear AC-OPF rather than DC for real power dispatch, and state-of-art data, and it's pretty poor also. So we did our own simulations. The other ones for showing how, for example, wind integrates with load is it's really interesting how it evolves. One student was doing decision making for wind, and so you develop this distributed stochastic optimization for wind. And you see that at the same time, another student is doing the same thing for adaptive load management. And then you put them together through the grid simulator, and they talk to each other. So one of the open questions that we are just about to engage in, how do you do more general smart grid simulator to have a really user-friendly platform to have these interactions, you know.
Is it publicly available?
Yes, and this is actually this smart grid simulator that I show was the basis on which we got our center, you know, because I think it's the first time that it was shown. Yes.
My question is on the last bullet. I mean, you mentioned that the cost benefit should be analyzed. What about if the costs were higher than the benefit? Then you should not be involved.
Right, and it got lost because I was talking about a lot of things, but somewhere there when I was talking about transmission as an enabler, we talk about transmission as at value. So there is a break-even point between the cost of the IT and the next. So there are break-even points between several things. One is how much would you gain by building the new new power plant versus being inefficient day after day, you know, because you don't have that. Or the break-even point between putting hardware or putting IT. All that needs to be analyzed. And part of the problem is, you know, I didn't talk much about this, but part of the problem is that there is no single decision maker, so people push their own technologies. So the aggregators are going to be extremely important in the future because they rebundle the value and they look for the best deal and then everybody wins. But that is to be done.
But do you think eventually, I mean, the benefits are going to be higher than the cost?
No, not necessarily. Not necessarily at all. It depends, you know, really, I have no clue about large systems. These are just, you know, toy examples that we are playing with. Actually, the ones that I talk about, the regulated industry, we have simulated, this is a little bit outside of university work, those estimates, 10, 20% efficiency savings on reserve, that is for at least 10 US utilities, real utilities. Yeah, so I mean, the cost of IT there would pay big way. Yes.
So for the different kind of systems like the physical grade IT do we identify the interaction variables?
Yes, I'm glad you asked that question. So the question was, for different types of systems, that's really one of the key ideas in the talk, that there are these bulk power system, regulated or restructured or completely distributed. They all have different type of interaction variables, and you need different aggregation. So things that I haven't talked about, which are really exciting and we don't know the answers to, is how do I compare 1,000 micro CHPs with one large generator, right? And how do I actually cluster the neighborhood with 1,000, micro CHPs, so that I actually count it against building another large generator? And we don't know how to do that well, because it's not just capacity. Maybe these distributed guys are more reliable. You lose one, you're not going to lose everything. You need fewer or less reserve. Maybe something is cleaner. Traditional methods for doing that cost-benefit analysis don't exist. On the interaction variables, it would be, I think, I always sell this PhD thesis. Always the list grows bigger and bigger. So how would you do the aggregation the right way, so that by the time you're aggregating, you just have a little bit overlap of interactions, which is not much, and then you don't need coordination, or you do smaller aggregation, or you even do it dynamically as conditions change? I mean, this is the future of IT, and we are just not thinking that way. You can, on the fly, aggregate users and have them talk to somebody else if you have the right information. And so the interaction variables, by definition, they're well understood. I draw the boundaries, doesn't have to be utility. And you can actually derive the interaction variables, which are function just of your own subsystem, so you know what's inside. And they are not going to interact with the rest of the system unless you connect it. So you know what the definition is. And then you can bottom up see how far you need to aggregate. But that's all work to be done. Bruce.
When you talk about saving reserves, it makes a lot of sense to do that. However, that's the inefficiency is not something that directly affects the utility. It more becomes part of the rate base. Is that correct?
Yes.
And so how do you get, say, the utility to step outside the comfort zone when it's something that is going to be passed on? It doesn't directly affect their profitability, shall we say.
So maybe some of those efficiencies that I talked about, which I said we've studied it on some real systems. It's taken since 2001 to maybe convince some utilities that this makes sense. And actually, right now, it's an interesting period because smart grids have to do something. You need to use these PMUs for something. So you better show that you're doing it differently. You're doing the cost reduction or something on behalf of your customers. And that's something that utilities are not used to, and they have to get used to it. So the incentive will come sort of an indirect way, but it's not there yet. It's sort of almost pushed by the technology. You have spent money on these high tech. You better show something that you've done for customers. And I think this is one of the most difficult questions that utilities have faced now, because they took the money for stimulus, they promised they'd do something, and right now nothing is being done. So I think that some utilities, forward-looking utilities, are looking into this. But you're right, the incentive is not explicit. Yes?
So another question about accessibility. Is that about the trade-offs inside one system, or that actually can cross into another system, like the trade-off between designing a Phasor grid and the policies?
Yeah, all of that. The thing that I guess I meant the most by this is that even in the regulated industry, the only objective that you have now is reliability, right? And cost happens to be whatever. It's like a secondary. It's really a constraint. So can I change? OK, these are very simple examples that you can do with IT. The system is in normal conditions, right? There is no danger of going into blackout or anything. Is it at that time that I can switch adaptively to the performance objective to increase efficiency, to use cheaper or cleaner power plants? When I'm closer to the limit that there's some reliability problem, then I switch to managing extreme voltages. And so if I'm very smart in my IT on which even technical objective I use, I can make quite a bit out of it. We don't have right now sort of commercial user-friendly software that's switching between objectives easily. But people are developing it.
So in terms of modeling, it's like we have all of the constraints under one problem, or it's kind of switching from one problem to another problem?
It depends. You can take sub-cases, or if you want to, even I don't dare to do the most general case, because it's really a heterogeneous system. There are so many dimensions. But the point is that there are such strange interdependencies between information, financial signal, policy, and technical that we better think about it. Yeah. Michael.
Thank you. Very interesting talk. Most of the information technology and the science, power systems, and so on, and the software, etc., has been focusing on the high voltage transmission system, it seems to me. And Phasor measurement units will allow us to be able to handle better the routing, perhaps the regulating the distance, the electrical distance of lines and all that stuff, and avoid blackouts. However, a lot of the action is taking place at distribution network, where we do not have, to my knowledge, and please correct me if I'm wrong, we do not have well-established power flow models. For example, I haven't seen a single-phase power flow model. We don't have IT, we don't have sensors and so on to the extent that we have been investing in and have been learning and knowing how to control, have been teaching in schools and so on. I don't see us teaching very much about the distribution network, which is, I think, going to play a very big role. So do you see a paradigm shift in educational institutions as well as in IT and technology and so on that is going to focus at the distribution network, which now may be more adaptive. Up until now, demand we were considering as monolithic, as sort of following certain profiles. But hopefully all of these things are going to change. What do you see the impact? I mean, can you say a few things about the impact of this on education institutions and on technology and so on?
Well, I think it's really interesting. I think you're 100% right, and this actually opens opportunities for a lot of people who are not really in the domain, in the traditional power systems, for developing concepts for monitoring, for distributed control, for protection, reclosing, the topology changes, etc., at the distribution level. So it's all there that should be done, and I think those are, and they're coming. The stimulus money actually has opened the door for that. The part that I stressed, there was one line there, is that, again, there is an interaction variable between the distribution system and transmission system that must be captured in order for the distribution system to have incentive to do that. So if you do all the intelligence at the distribution level, customers should be paid for not building that new power plant. And we really don't have that in place now. So absolutely, we have to teach these courses from scratch.
Institutions stepping up to the plate to provide this
we happen to we happen to have a project that's just starting now with actually with IST in Lisbon, and they have been. Europe is much more ahead in the distribution automation than the U.S. and they already have version of distribution power flows and everything before you add the new intelligence in Electricity Portugal. And so we use that, and they teach that there. We sort of, the US has completely fallen out of.
We don't want to do that because it's very socialist.
No, I think that you are absolutely right. I think the education is, it's a fantastic opportunity to, these are sort of toy examples of distributed systems, right? And how much you can do with different intelligences. And I think that's how one should actually think about it. But there are some, right now, I mean, the reality is that there's not much happening at the customer side because he doesn't see the signal that we were just talking about. So it's, everything has to be revisited. Yeah. Yes?
There are models for the hardware in terms of reliability, and pretty
Right.
well established. How about for IT? Do you have models about the reliability for IT if you introduce a substantial amount of IT into the chain of power systems?
No, it's really an open research area completely. Even on the power electronics question, people are asking, it may be much less robust in the harsh environment, etc. No, very little work has been done on that. One tackle that I've seen is that people think with these distributed sensor networks, you have so much redundancy that actually is going to be more robust than the traditional centralized ones.
But suppose the control process, some of the links that for your interactions, they fail in an information sense, not in the power hardware sense.
Absolutely, and this must be addressed. Yes, absolutely.
Okay. I think we are out of time, so I'd like you to please help me thank Marija again for a wonderful.
Thank you. Hi.
Hi, I'm Rich Koloshinsky. I'm with
Hi.
the Draper Laboratory.
Yes, hi.
So I'm doing a lot of work with Ken Laparo. So
Oh, yes, yeah. We were supposed to connect. Yeah. Did this make sense?
Oh yeah. Actually, one thing I was thinking